Hello students, this is Mr. McAllen, and today we're going to be working on the last section of our textbook where we're talking about how to find functions from different places. For instance, the first thing we're going to do is how do we find functions from formulas? How do we find functions from graphs? And then we may not go over these examples, but sometimes you have functions that you get from verbal descriptions and you get functions from data. We're going to focus primarily on the first two bullets of this, and tomorrow in class we'll do some other problems with the second two bullets. So anyway, if you look at the first problem, we have an example where they want us to write the area of a circle as a function of radius, diameter, or circumference. So a lot of times we just have this formula memorized. We know that the area is equal to pi r squared. So using function notation, we would say area is a function of radius, and that equals pi r squared. So that's something that we would get off an equation sheet. You should have that memorized by now. But if you want to turn this into a function of diameter, you have to do a variable switch. So you remember the formula for diameter. How does that relate to the radius? And you remember the diameter is equal to 2 radii. So if I want to make a formula, area as a function of radius is equal to pi r squared, I've got to replace the radius so that it's now the diameter. So I'm going to replace the radius with d over 2, and then I'll rewrite my area equation as a function of diameter now, which will just be pi, instead of radius, it's going to be d over 2 squared. I have to simplify this, and I get pi d squared over 4. You might be like, well, where's the 4 coming from? Well, the 4 is coming from squaring 2. 2 squared is 4, and this would be my area as a function of diameter. The last part is they want us to write area as a function of circumference. So area as a function of circumference might be a bit trickier. So let me just start out with what I remember. Area as a function of radius is pi r squared, and I have this formula that I'm always given for circumference. Circumference is 2 pi times the radius. So if I solve again for the radius equals circumference over 2 pi, I can plug that value in for my radius here. So area is going to be transformed to a function of circumference that'll equal pi. The radius is going to be replaced with circumference over 2 pi, and I'm going to square that. So my end result for area as a function of circumference will be pi circumference squared all over, now I've got to square the bottom, I've got 4 pi squared. The pi squared cancels with the pi, and I'm left with just circumference squared over 4 pi, and that would be my area as a function of circumference formula. Moving on to the next problem, we'll just read the example. This is straight from the textbook, Finney, Domena, Waits, and Kennedy. I want to give them credit for some really good examples here. We have another problem where we're going to come up with a function from a formula, but they give us a scenario. So read the question, read the example, and we'll do it in a second. I'm just going to pause the video so that you have a chance to read it. Okay, hopefully you had a chance to read that over. I read it over while you were reading it, I guess. Well, this is a video, so who really knows? So, all right, so what we have is we have a flat sheet of cardboard. And the cardboard has certain dimensions. Its long side is 15 inches, and its short side is 8 inches. And these squares are cut. They're each x by x. So it's really tough to visualize this if you've never seen this problem before. But basically, if I look over at this drawing, this side right here when I fold up the box, it'll be this side right here. And the height is going to be x as you go around the box. So what we need to do, because they want us to come up with a volume equation. Actually, they didn't really ask us what they want to do. We want to find the value of x that will give us maximum volume. All we really want to do right now is, can we come up with a function that will give us volume as a function of x? So hopefully you remember a formula that you were given a long time ago for the volume of any box is that you have length times width times height, and that will give you, if I write volume as a function of 3 variables, yep, and I can put in parentheses comma, right? It's just like L, W, H. We want to convert that into volume as a function of x. So we have a way to do that. If I erase this, what I was writing on the side, I'm going to leave the variables in so I know what everything is. So we look at, we've got this is x, and this is x, and these up top and on the bottom are x. This distance here, though, is 15 minus 2x. The width, that's from left to right, it's tough to see. I'm going to put that dimension out here. That width is going to be 8 minus 2x. So this dimension will be 8 minus 2x. This dimension here, the long dimension, will be 15 minus 2x, and the height is x. So if I want to write the volume of a box in terms of 3 variables, I just will write it as the length is 15. The length, which will be this, is 15 minus 2x. The width is 8 minus 2x, and the height is x. Now if I want to see what the maximum dimension for this box would be, I can use Desmos to do that. I can also plot this function on my graphing calculator. So I'm going to just pause the video and go to Desmos so I can show you how to do this. Okay folks, so I'm back and I remember the formula. So I'm going to put in volume as a function of x is equal to, the first part was 15 minus 2x. The second part was 8, for the width was 8 minus 2x, and the height was x. So I'm going to look at my, if you look at my, basically if I zoom all the way out, I can see I have a crazy looking function. So I've got to change kind of my window settings. So I want my window to go from 0 to, I've got to think about what a reasonable domain for this problem is. X can't go to infinity, but in fact x can't go beyond the value, if I look at this part, x can't go beyond the value 4, because if it goes beyond the value 4, I've got a negative dimension. So I'm going to really concentrate on setting my window settings so that my domain is better. I'm going to go from 0 to 4, and my y-axis, you could see, is okay. And what I have here is I show the crazy shape of a cubic function, but this is what I'm more or less interested in, the space from 0 to 4. And you can see that I max out at a dimension of x is 1.667, or 1 2/3 inches, and the maximum volume will be 90.7. So I'm just going to cut and paste that. So this would be the setup to find my maximum volume. And at later years in math, like next year when we do calculus, we're actually going to show you how to use derivatives to do that. But that would right now represent what the maximum volume would be of 90.7 cubic units. The last problem here, I just would like you to read it over before we start doing it. It's about protecting an antenna inside of a satellite dish. This is actually a really interesting problem, and it's going to use parabolic equations or parabola equations. So anyway, take a moment to read it, and then we'll work it out together. Okay, folks, so we're back, And just to show you, like this is a I'll draw it on a slant, but this is basically like a parabolic dish, and you normally you have like an antenna on the inside of your parabola, and when you ship these items, you want to protect that antenna-like device because that's where all the sensors are that do all the important stuff. The dish actually does all the reflecting to magnify the signal right in the center there. What they're going to do is they're going to take a cylinder. That's a piece of cylindrical cardboard that looks like this, kind of like we all know what cylinders look like, but it's like a piece of cardboard that's going to fit right inside here over top, and we want to pick the right height so that when we sit it in there, it's perfectly flush with the top. Sounds pretty complicated, but it's actually not too bad. This shape here, because it's a parabolic mirror, is a parabola. So what we want to do is, and the diameter is 24 inches, and the height is 6 inches. So we want to find the right size of cylinder to make this all work. So that being said, the best thing to do here is to make a graph so we can actually see the parabola on the XY plane. And we see here, this is the same surface here as is here. And we really want to set our dish, our cylindrical cardboard piece right there where I drew the box. So how do we find the right size so that we can do that? The cylinder has a diameter of 12 inches. So we know that it's going to go from, it's going to go 6 to the right and 6 to the left. So we know that what that size is, but we need to find out, for this, what is the height of the cylinder. So this is how we do it. We got to come up with an equation of the parabola. So y equals kx squared. We have a way of calculating what the k should be, because this is just this could be ax squared like in a normal quadratic equation. So we can calculate that. So we're going to put in 6 for the y value, and we'll have a, and I'll put in 12 for the x value and square it. So my a value is going to be, for the parabola, so I can come up with the equation of the parabola, my a value is going to be just 6 over 144, which would reduce, if you're good with fractions, to, well, this will be 3 over, I'm going to take a factor of 2 out, so this will be 72. And I think 3 goes into 72 also, so that's going to be 1 over 24. So my equation for my parabola is y equals 1 over 24 x squared. So now I want to come up with what my cylinder height would be. So all I need to know really is I know it's got to be, if I were going down to the bottom here, that would be 6 units long. I need to find out how high is my parabola at that point of 6. So to find that out, if I plug in y equals, I do 1/24 of 6 squared, because I'm at the value x equals 6, I'll find out how high the parabola is above the x-axis. So that's what I'm looking for, is that height right there. So that height is the y value. So here y equals is 1 over 24. I've got 36 because that's squared, so 36 over 24. That's going to be, if I take, 12 out of both, I'm going to get 3 over 2. So that height is 1.5 inches high. So if I know that's 1.5 inches high, and I need to have on the y-axis, we need to go up to a height of 6. Right? Well, that's like really over exaggerated, but we had to go up to a height of 6. So I know that my remaining height of that cylinder is going to be the difference. So basically 6 minus this h will give me the height of my cylinder. So 6 minus 1.5, the height of the cylinder has to be 4.5 inches tall. So I know this was very complicated, very not such a usual problem that you do, but this next section that we do is going to be all about modeling different scenarios with equations, and there is definitely an art form to coming up with these equations. Tomorrow in class we're going to be working on this quite a bit, and so I hope this video helps you understand what we were trying to do, and I'll give you a couple problems in the form to see if you can do some basic modeling. So look forward to hearing your comments, and see you tomorrow.